Today we'll review for the exam. The exam is tomorrow during laboratory time. The exam is on chapters 4 through 8. Leslie, question? Yes, I am recording. I will even double check because I'm always embarrassed when I'm not recording. If I click here, we should have two windows. That second one, to the one on the right, says it's recording. It's worth checking. Emily has a question.
What time is period?
I do not know. It should say on Moodle in the announcements, I think. But I do not know offhand. Yeah, go ahead and somebody look in the announcements on Moodle, and you can just go ahead and raise your hand when you find and let me know so I can tell everyone. So before I start review, I said I was going to show you the answer. Okay, that was genius of me. I forgot. I am in a different program. Not the one where that works. So I have to go like this. Which one will win if they roll without slipping? Now, as you saw just before we started, I practiced a few times taking out the cylinder because I think the cylinder was dealing with some other issues like air resistance. Here I have 3 balls. 2 of them are solid, relatively speaking, the golf ball and the metal one. And then we have the tennis ball that is hollow. You see the 2 solid balls easily beat the tennis ball. So that we can see without any ambiguity. And so we're going to figure out why they don't come down at the same time, why one's faster. There are 2 ways of doing this. Both of them are ways that are appropriate for preparation for the exam. So the 2 ways, well, what do you think the 2 ways will be? Just shooting from the hip. What do you think the 2 ways of solving this question will be? Yes. Putting in some numbers. Not really one of the recognized physics methods, but we're going to do that. Well, actually, we're not going to put any. We'll put in one equation into another equation. We won't put any numbers in. Any other ideas? Well, we're going to be studying 2 primary ways of solving dynamics problem. Well, we're going to be tested, I should say, on 2 primary ways of solving dynamics problems. Those 2 problems are Newtonian dynamics, that is using Newton's second law, and work energy relation. So I'm going to solve this problem both ways so you can see examples of how to do the problems. So I put over here the little form that we used in lab when we did problems with the Newtonian dynamics. So I'm going to follow the directions there. Michael? So I'll draw a physical diagram here. Here's the ball. Draw the forces acting on that. Force of gravity equals mg. Force normal, that's unknown. Force of friction, that's unknown. They rolled without slipping, so which kind of friction was that? Okay, if there's no slipping, it's static. If the surfaces are slipping, it's kinetic. We don't know how big that force of friction is. There's no way to calculate it with just a simple equation. We're simply going to have to say it's whatever force is necessary to keep it from slipping. So I don't have any equation to substitute in there. You do have an equation that says force of static friction is less than or equal to mu times force normal. But that's just setting the maximum limit it can have. It's not saying what its size is going to be here. So there's my physical diagram. My free body diagram will be like that. Notice I have two arrows coming in and one going out. I don't find that really important. Some people do. Obviously, I don't, or else I would have been more careful with it. I need to identify a coordinate direction. What's the rules we use for identifying the coordinate directions? They're up here. Okay, if there's acceleration, I want one of my coordinates parallel to that acceleration. So in this case, we know it's going to accelerate this direction. So I choose my directions. I wrote A for, I'll call it X. X is the direction it's accelerating. Y is the direction normal to that. So immediately I can say my AX is equal to, I don't know. My AY is equal to 0. Leslie has a question.
So what do you mean by slipping?
Slipping would be if it went like this, that would be slipping, right? Because the surface is slipping on.
Would it say that it's slipping? Or?
It would probably say something. Okay. Whereas here, it's not slipping, it's stationary. Everywhere where this is touching the board, it's stationary, just for a split second.
So when it's slipping, then it's kinetic? Or?
Then it's kinetic, okay. That's right. And then when it's kinetic, you have mu times force normal is the kinetic friction. Okay, so I have the acceleration. Now the next step. The next step, now you're not going to have this form on the test. You should have these steps in your head. The next step is probably the one that's most difficult, breaking the forces into the components. And so I have three forces, which I conveniently did not label here. There, now I've conveniently labeled them. So I'm going to have force of gravity in the x direction equals, and that's the one that takes me to task. Force of gravity is vertical, but my coordinate system is not vertical. So I'm going to take my dashed line so this one was parallel to the y direction, this one was parallel to the x direction. It makes a right angle here, that's what that thing's supposed to be. And so my vector components go from here. Oh, wow, that's a fine straight line. And then we have to look at what angle do I know. I know, well, let's presume I know this angle. If I knew that angle, that would be, we take this angle here, well, yeah. This angle here is the complement to theta, so this here is 90 degrees minus theta, which means this angle here is theta. And so then breaking into components, my x component here is the opposite side. How do I know my x component is the opposite side? Let's start with the easy question. Which side is the hypotenuse? The force of gravity. This is the hypotenuse because it's the side opposite the right angle. Since this is my angle theta down the bottom, the opposite is over here. And since x was in that direction, that's force gx. So force gx over mg, opposite over hypotenuse, is sine theta. Hence, 4gx is mg times sine theta. Wrong one. We have to make sure we determine, is that positive or negative? So when I look at my arrows, my red arrow for the component force g in the x direction is down and to the right. My x direction is down and to the right. Since they're the same direction, that makes it positive. Now for the y component is going to be here. Is that going to be positive or negative? Somebody said negative. Negative because y was pointing up to the right. Force gravity y was pointing down to the left. So opposite direction's negative. That's the adjacent side. breaking this into another piece that we'll talk about in a minute. That's the piece that is not going to be on the exam. So I have force of gravity broken into components. The other two are kind of easy. What is the force normal broken into its components? How much of force normal is in the x direction? None. How much is in the y direction? All of it. Okay, so that was like pretty easy. I like things easy. What about the force of friction? How much of the force of friction is in the x direction? All of it except negative. And so in the y direction, it's going to be that's right. Somebody said 0. So now I've broken the forces into their components. Why did we break the forces into the components? So we can apply Newton's second law. That's the only reason we broke them into components, so we can apply Newton's second law. So I have sum of the forces in the x direction is equal to mass times acceleration in the x direction. Copying down, that gives me mg sine theta minus force of friction equals ma. Since acceleration in the x direction was a. I do not know the force of friction, and I don't know the acceleration. So this equation is done for now because I don't know the things there that I highlighted. So I move, that's better. So I move over here, go the y direction. Once again, reading down, I have this. Well, this does allow me to directly calculate force normal. But the sad truth is I don't care about force normal for this problem. That wasn't one of my goals, and force normal isn't in this equation for the acceleration. So I have to go one step further, and I'm going to have the torques. Now, if you want to be all technical, the direction of the torque is x cross y is z. So this is actually summing the torques in the z direction. The torques part is the new part, stuff that won't be on the test. So I'm going to have torques due to each of these forces because remember, torque is equal to R cross F. What is R? How do we calculate these? We need to decide where we're going to sum the torques about. I'm summing the torques about the center of rotation, which would be the center of the object. And so R will be the radius of the object. And it will be the vector that points from the center to where each force acts. So I got to come and look back at the first picture. The free body diagram doesn't really help me with the torque calculation because I need the locations. So looking at the first picture, here's my center of rotation. Remember, R cross F is taking the perpendicular distance between the R vector and the force vector. That is, where the force vector acts, how far do you have to go perpendicular to that to get to the center? Well, if you look, force normal is acting right on the center. That is, the line goes through the center of the wheel, which means the perpendicular distance for the force normal is 0. Thus, the torque for force normal is 0. Likewise, force of gravity acts right through the center, so the perpendicular distance for gravity is 0, so the torque from gravity is 0. So I can quickly put the torque from gravity equals 0, and the torque from normal equals 0. What I'm left with is the friction force. The friction force, its line of force as we call it, its closest approach to the center of the wheel is the radius of the wheel. Hence, the perpendicular distance is the radius of the wheel, or radius of the ball, or radius of whatever the object is. So that torque is going to have a magnitude of the radius of the object times the force of friction. But notice I said it has a magnitude of. I need to pay attention to direction. Determine if it's a positive or negative torque. So looking at this picture, and I will write in the R vector. There's the R vector. Here's the force of friction vector. Using my right hand rule, I take my right hand, make my index finger point parallel to R, and then keeping my index finger pointing that direction, I rotate my hand so I can make my middle finger point in the direction of the force. And so it's like that. My thumb points in. My thumb points in. What does that tell me about the sign? Negative. And so I have the torque due to friction is negative radius of the object times the force of friction. Now there's a couple relationships that I need to establish. And the first one is the relationship between acceleration and angular acceleration. And we've learned that angular acceleration is equal to acceleration divided by radius. But once again, we have to make sure, is it the same radius that we were talking about before? Yes, it is. And if it accelerates in the positive direction, the angular acceleration, well, I've got to do it for you. If it accelerates in the positive direction, the angular acceleration is going to be clockwise. Is clockwise positive or negative? Negative. So there's a negative sign in this relationship based on the directions that we define for our axes. So that means alpha is equal to minus A over R. So now I apply Newton's second law. Sum of the torques is equal to I alpha. Reading down here, that's minus R force of friction equals I times minus A over R. Or solving for force friction, force friction is IA over R squared. Now I'm going to take this force of friction and substitute it right there. So I'm going to have combine the A's together. Do that by just adding IA over R squared to both sides. And we have that relationship. Or finally, for acceleration, there's an equation for the acceleration. Not actually done for final speed, which is really annoying. How would I get to final speed from acceleration? I would use a kinematic equation that says v final squared minus v initial squared is equal to 2a delta x. But since v final squared is proportional to a, the one with the higher acceleration is going to have the higher final speed, so I'm going to stop here. All I have to do now is say, since I is in the denominator, a bigger I means a smaller a and a slower speed. A smaller I means a bigger a and a faster speed. So I look at my original problem, and the one with the smallest I should win. So I have 2/3, 1/2, and 2/5. 2/5 is less than 1/2. 2/3 is bigger than 1/2. Hence, it should have been the solid sphere that wins. The hollow sphere, the tennis ball, comes in last, and it should have been the cylinder in between. That's doing it with Newton's second law, Newtonian dynamics. I've used up 20 minutes of the class period. I've worked a problem that is beneficial for you preparing for the test, so I don't feel bad about that, But you see that took a long time. Agree it took a long time?
Yeah.
Okay, there's a second way, work-energy relation. I have the steps for the work-energy relation shown down below. I'm just going to do it here. When you're doing a work-energy problem, the first thing you do is you draw your problem with the beginning and ending points. And then you identify the kinetic energy initial and the potential energy initial, and the kinetic energy final and the potential energy final. So it starts from rest, and let's say that it goes down a distance h. Starts from rest, so what's the kinetic energy initial?
0.
0, right, because it's 1/2 mv squared plus, now the 1/2 mv squared is stuff that's appropriate for the exam. This whole picture and how to solve it, appropriate for the exam. But there is an additional kinetic energy part that's new. Won't be on this exam, but something you're going to need to know for the next exam. You have 1/2 mv squared and you have the rotational part. So the T stood for translational. That's traveling in a path. 1/2 I omega squared. And just like before, omega is equal to minus V over R. So this is equal to 1/2 I V squared over R squared. So V was 0 in both cases. So kinetic energy initial was 0. No problem. What about the potential energy initial? What's the equation for potential energy? Mass times gravity times height. Force times distance, right? Work. So here its height is h, so it has potential energy of mgh. Then I get my final values. My final kinetic energy, 1/2 mass V final squared plus 1/2 I V final squared over radius squared. And potential energy final, 0. So work energy problem, you first draw the picture with your beginning and ending points. If you have more than 2 points you're interested in, like if you're like, what's the speed here and what's the speed here? At each point of interest, you want to put the kinetic and potential energy. The next step is identify, is there a non-conservative force? Actually, more importantly, is work non-conservative equal to 0? Work non-conservative is work done where you don't get the energy back. So it's got to come from a force. We've already identified the forces acting on it. We have force normal. The force normal does no work because the direction of motion parallel to normal is 0. We have the force of gravity. The force of gravity was conservative, so that's where we got the potential energy. It does no non-conservative work. Its work is all conservative. Then we have the force of friction. It wasn't sliding, so the distance that the surface moved was 0. Even though the whole thing was rolling down, the surface wasn't moving there where the contact was. And so there's no distance for the force friction, hence no work from that. So we have work non-conservative is equal to 0. If it was sliding, it would not be 0. If somebody was pushing on it or you had a motor working on it, then it would not be 0. But since it is 0, we're happy. It makes life easier. And then we apply the work-energy relation. Work non-conservative is change in kinetic energy plus change in potential energy. 0 is equal to kinetic energy final minus kinetic energy initial plus potential energy final minus potential energy initial. Putting in the values I have up above. Kinetic energy initial was 0, so that's where that minus 0 is. Potential energy final is 0. potential energy initial was mgh. Now this is easier because I have V final right in my equation. So I'm just going to move mgh to the other side of my equation. And I have mgh equals 1/2 mv final squared plus 1/2 I V final squared over R squared, or it's equal to V final squared times 1/2 times M plus I over R squared. So solving for V final squared, I have this relationship. Now, of course, I would square root it to get to V final. But once again, the larger V final squared, the larger V final is. We again see V final is inversely proportional to the moment of inertia. So the one with the smallest moment of inertia is going to have the biggest V final. The one with the biggest moment of inertia has the smallest V final. So we see the same relationship. We have our equations all straightened out. Which method was easier? This one. This one was clearly much easier. No resolving vectors into components. No combining equations, really. I mean, I had to put them into that work non-conservative is equal to change kinetic energy plus change of potential energy, but it was a much simpler process through. So usually, if you can use the work energy method, you want to use it. If you have a work non-conservative, that is if something like it's sliding, then it's going to be a little more difficult because you're going to have to calculate the work non-conservative and it's not equal to 0 in that equation. But still, it's generally going to be the easier method. Some cases, work energy method will be the only one available to you, just you wouldn't be able to solve it with Newtonian dynamics. Any questions about the two ways of solving the problem?
If there is friction, is the work energy still viable?
Yes. It's just like, let's say that I'd had a block instead of a ball. We'll make it a block. And the block was sliding down. Okay. Here's my block for today. And the block was sliding down. So it has a force of friction that's going up. And then I take that force of friction, which I need the force normal for. So I would have to go to my force part and find force normal, which came out pretty simply. And then from that force normal and the coefficient of kinetic friction and the distance that it slides, I would calculate the work done by friction. And you have to keep in mind the direction. The motion is this direction, the force is that direction, opposite directions is the negative work. So the work non-conservative would have been negative in this case. Okay, so it took about 6 minutes to do the problem of work energy. It took about 20 to do it with forces. You can see the difference there. Now let's get to actual review. And do remind me, I can't move forward, but did anybody look up the time for tutoring?
I can't find it. I think she only mentioned it in lab that one time.
I will send her an email and make sure that there's some kind of announcement that you get to tell you about tutoring today. Okay, yes, Mike. I believe so. I thought she sent out an email, or I thought she put it in announcements, but it must have been an email. But I will check. Yes, the time has been established. Yeah.
And she mentioned rescheduling it last Thursday at the very end of tutoring. She mentioned scheduling this one to you earlier. Except I don't know if she ever did.
Okay, I will check, and I will post it on Moodle, which should send an email to everyone as well. Okay, so things that are on the test. Notice I put drag and Stokes' law in italics. I'm not going to have questions asking you to use drag equation or Stokes' law equation. You might just have, it has a drag force of this value, but you won't have to use the actual drag equation. But you should be able to define, what the force of gravity is, spring force, normal force. Remember, normal doesn't mean regular. It means a specific direction. Friction and tension. Tension, remember, a force is being transmitted through a cable or something. Its direction is always parallel to the direction the cable leaves the surface, and its magnitude is equal to the tension. So the force applied by tension, magnitude is tension, direction is the direction it leaves. Friction, we've talked enough about that today already, normal. Spring is always a restoring force. You stretch the spring, it pulls it back. You compress it, it pushes it out. Gravity, on the other hand, is always attractive. It's always attracting things together. Know Newton's 3 laws. I am not going to ask you which one is Newton's 3rd law. Right? It probably is good for you to know, but I know that when I was in college, I was just happy to know the 3 laws. I didn't pay attention to the order. Some people are more organized than me and do. As a teacher, of course, now I do. But you do need to know the 3 laws. The first law being the law of inertia. An object in motion, stays in constant motion, unless an unbalanced force acts on it. The second law gives you the equation. It says the net force acting on an object is equal to its mass times its acceleration. And remember, I'm really a stickler. It has to have the summation or the word net. It's not F equals ma. It's sum of F equals ma. And then the third law, for every action, there's an equal and opposite reaction. That means that if a car hits a person and puts a force of 20,000 newtons on the person, then the person also hit the car and put an exact equal force of 20,000 newtons on the car. They put the same force on each other. They're not going to respond the same because the person is soft and squishy and the car is not. So the response to the force is different, but the forces are exactly equal and opposite. Solving the equations, well, we've just gone through and looked at the steps to solving a Newton's 2nd law problem. But just one last look at the steps here. This is already posted on OneNote for you. You want to first draw your diagram to illustrate the problem, then identify what your object is you're interested in, draw a free body diagram for it, identify your coordinate system. If there's acceleration, choose so one coordinate direction is parallel to the acceleration. If there's no acceleration, then just choose the coordinates that are going to make it easier. If all of your coordinates are mutually perpendicular, choose the directions that make them so they're already resolved. If there's one that's not mutually perpendicular and the others are, well, choose the easy way. Make so you only have to resolve one. Then break your forces into components based on your coordinate system and apply Newton's 2nd law in each component direction and solve. So those steps are important. I'm not going to ask you what the steps are. I'm going to ask you to, show this or show that or, solve a problem for the last 3. And so having knowledge of them is what's important. Yes?
So you said for us who want to show our work, then we draw the picture, and then you want us to write down what we're going to use. Like, for instance, I will be applying Newton's second law to this.
Okay, so I will have how the score for manually scoring works on the test. So you won't have to have that memorized. But yes, for the concept part, you need to basically say how you're going to solve it so that it's clear that you have a plan. You're not just randomly throwing numbers and hoping that it works. So if it's correct, you could have a very concise, short explanation. Some people make it very long to make it super clear. Okay, so we've already gone through that. Chapters 4 and 5 were Newton's laws. Chapter 6, we introduced circular motion. That is, things going in a circle. And we learned that if something is going in a circle, it has to have an acceleration to make it change direction. And we call that acceleration to make it change direction the centripetal acceleration. Now, I was looking with Andrew, and the equation sheet has A sub r is equal to omega squared r is equal to v squared over r. R in this case stands for radial. And I believe that's what the textbook has is A sub R. And so I went with the textbook's nomenclature there. I usually put A sub C for centripetal. Centripetal means toward the center. R stands for radial, which means in the direction from the radius outward. Technically, there's a difference in those two. Centrifugal would be the same as radial. Centripetal is the opposite. Centrifugal is not a term that I use in this class for the simple reason that it's a fictitious force. Centrifugal means pulling away from the center. If I have my little bob that I swing around my head, it's very easy to say, oh yes, that bob is pulling away from the center so that I have this string pulling outward on my hand. But that is actually an incorrect explanation. What's going on is the bob is trying to go in a straight line and I'm pulling in to make it change directions. So yes, there is an outward force on my hand, but that's because I'm pulling in and the string's responding to me pulling in by pulling out. And so something would just go in a straight line if you didn't have the centripetal force pushing inward. The centrifugal term, we call it a fictitious force because there really is no force pulling the object outward in the circle. It's just inertia trying to make it go straight. So centrifugal is fictitious. Now remember I talked about in class on Friday. Centripetal force is the resultant. It's the sum of the forces toward the center. You never put the sum of the forces on your free body diagram. So your free body diagram should never ever have centripetal force marked on it because that's not a force acting on the object. It's the name we give to the sum of all the forces toward the center. Now in the case of swinging this around my head, there's only one force toward the center, the force of tension. So my free body diagram would have only the force of tension toward the center, or as we spoke about on Friday, technically it's the force of tension times cosine of the angle below the horizon axis. And that would be that sum of the forces toward the center, the tension cosine theta, would be my centripetal force. But it's not shown on the free body diagram. It's the calculation of the net force toward the center. Coriolis effect. We talked about the Coriolis effect in regard to storms like hurricanes. The Coriolis effect when air is being pulled in at the bottom for a hurricane, it starts to twist because you are moving closer or farther from the Earth's axis of rotation as it moves parallel to the surface of the Earth, unless you're right on the equator. And that moving closer or farther from the Earth's axis makes it so the relative speed of the air compared to the Earth is different, and it appears from the surface of the Earth to veer forward going north, appear to veer going south. I should say goes eastward if you're going north, goes westward if you're going south. And at the top, when the air comes out, you have the same effect causing rotation up there too. So the rotation of these storms is caused by the Coriolis effect. You can talk about a Coriolis force, but it's a fictitious force. The wind was just trying to go in a straight line, but the surface of the Earth was moving at different speeds, and that's why it appeared that it was veering. So there was no force making it change direction. It was just going in a straight line, but the Earth's surface going at a different speed. Once again, you'll notice the stress and strain. I do not believe I lectured about stress and strain, and so I'm not going to test over stress and strain. Chapter 7, work, energy, and power. Work, force, multiplied by the distance parallel to that force, or force dot distance. So only a force that has motion parallel to it can do any work. So force normal is pushing up from the ground. As long as the ground doesn't move, the force normal is not going to do any work. Hence, we often say force normal does no work. But as I said in class, in a case like an elevator, as the elevator is going up or down, the force normal is doing work. So you can't simply take the blanket statement, force normal does no work. So you should be able to calculate work two ways. One way graphically, one way with equation. So let's look at the graphical. If I have a spring, the spring is the standard one for a physics class. Well, let's do not a spring. Let's do something real. I talked about that experiment they used to do with shooting a gun at PUC and somebody missed. Actually, it was a .22 rifle. So they changed to using a bow and arrow. But since we're using a bow and arrow, the bow is storing potential energy. The bow stores potential energy not in a stretchy string, which is what I thought as a kid. I thought a rubber band would just make a much better bow than using a string. But in the elasticity of the bow itself, the rod that makes the bow. So when you stretch that bow, you are doing work on it, making it deform, but it's elastic. It will come back and return the energy. And these days, if you get a hunting bow, those things have all of these strings going everywhere with cams that are rotating not on the center. Has anybody seen one of those? Okay, we have a few people nodding their heads. Have you ever wondered why it's got that crazy string set up and the cams and everything? Well, the scientist is that part of the thing that makes people scientists is they're like, I wonder what the heck is going on. Well, here's the reason. If you put the force applied to the string or to the arrow by the string, so I'm calling it force string, as a function of the draw position, you get a graph that looks something like this. So as you're drawing, initially it's really hard. And then you get back here and suddenly the force you need becomes much lower. That's nice because when you get it pulled back like this, then you're doing your aiming. You don't want to be straining and going because it's so hard to pull. But you want it to be hard to pull in the middle because you want to get as much energy stored in that bow as you are strong enough to do. And so this here is going to be a level that's hard for a person to pull, whereas this level here is going to be easy to hold. The work done force times distance parallel is equal to the area under the graph. So the work done to pull it, which is going to be the energy stored, is the area under here. And so you calculate geometrically. So what we do is we generally say straight line, straight line, straight line. And then you break it up into nice geometric. There's a triangle, a rectangle, and then a triangle and rectangle. Okay, you can't see because of my color choices. There's a triangle. There's a rectangle. There's another triangle and another rectangle. And you take the area for rectangles base times height, for triangle 1/2 base times height. You add those all up and it tells you how much energy was stored. So you need to be able to do that. I do have problems where it shows a graph and says how much work was done going from here to here. And you have to know, oh, I just need to find the area under that graph and I'll be good. So you go from the starting point to the ending point, find the area under it, and that's your answer if it asks how much work was done. So make sure you can do that. Questions on that? I don't want people to be confused.
So basically, you need to know how to calculate the area for that particular point from point A to point B underneath the graph.
Yeah, how to find the area from point A to point B.
Using the work equation.
Yes. All right. Be able to evaluate when work energy is easier, which is almost always, than Newton's second law. Now, brings us 5 minutes for our last chapter. Oh, here's the steps to solving work energy. I told you I would show you the steps later. Here's the basic steps. Draw your diagram to illustrate the problem. Right? I drew my diagram at the top and at the bottom because it was going from top to bottom. Then identify the energy at each important point in that problem. It was just comparing the top with the bottom, so I only had to put the energy at 2 places. Then I determined if there were non-conservative forces, and if so, how much work they did. In the problem I did, there was no non-conservative force. I think it was James that asked about what if there was a non-conservative force, and I gave the illustration of it sliding down and how I would have to calculate the work non-conservative that was done. And then you use the work-energy relation. This is the way that I almost always use it. The other form is work net is equal to change in kinetic energy. Remember, potential energy is defined as, those three lines means defined as, minus the work conservative. And so if work net is equal to work conservative plus work non-conservative, then that's equal to minus change in, minus change in potential energy plus work non-conservative. And that gives you this equation. So the two are indeed the exact same relation. They're just different ways of writing it. So you use that work-energy relation, and then you solve. And overall, like I said, that's easier because no vectors involved. Finally, chapter 8. You won't have to calculate the center of mass. You do need to know why it's important. That's where you can treat as if gravity is acting at the center of mass. It becomes important when we do torques, right? The center of mass is the thing that's going to follow, like a parabolic arc if you throw it through the air. So I gave the example in class, if I threw something like, I don't remember what I threw, but it was something long, it's going to tumble around, but the center of mass is going to follow the nice parabolic arc. Linear momentum, mass times velocity, it is a vector. You need to know when linear momentum is conserved. I'm going to give you a question that has like 7 or so different scenarios and ask in which one is momentum conserved. And so you'll need to look at, first of all, what did I ask for momentum to be conserved about? A simple example, if I take this ball and I drop the ball, is the momentum of the ball conserved as it falls? Yay or nay? Okay, I heard a strong nay. Why a strong nay? Okay, his answer was because it didn't come up as far. That has to do with energy, not with momentum. Energy was not conserved, he can tell, because it did not come up as high. But looking at momentum, what was happening to the momentum of this object as it was going down? It was increasing, it wasn't staying constant. So the momentum of this was not constant as it was falling. And of course, when it came back up, the momentum was the opposite direction. But if I had said the momentum of this ball and the earth combined, then it would have been conserved. As the ball falls, the earth is falling upward to it. How do I know this? Because Newton's second law says the change in momentum is equal to the net force multiplied by the time over which it is acting. And the net force between the ball and the earth is 0. The only thing acting on this ball is the earth and all occupants thereof. And the only thing we ignore, the sun, the moon, and the heavenly bodies, and we say the earth is only acted on by this ball, and so the net force between them is 0. So you have to pay attention to not just what's in the problem, but what system you're asked to find if it's conserved or not. Then be able to solve one-dimensional collision problems. I have a collision problem here, but clearly in the no time left, I won't be solving it. When you're solving these, you need to identify, is momentum conserved? And our rule is if it's a collision, during the collision, momentum is conserved because delta t is so small. Right? If delta t is approximately 0, momentum is conserved. Or if the net force acting on the system is 0, momentum is conserved. Then you apply your conservation momentum equation along with, if it is conserving energy, your conservation of energy equation. If it's sticking together, then you have the V final. So you have to pay attention to which condition it is, elastic or inelastic, and then solve. All right. Have a great day. I'll see you I'll see you here for the test tomorrow during the lab period.